right, doesn't this sound important? The fundamental theorem of calculus. Okay, it's like boom, boom, boom. All right, so we have arrived at the fundamental theorem. All right. The fundamental theorem of calculus, there's actually two parts to this. We're going to deal with part 2. I'm going to teach it to you in the opposite order. The order is irrelevant, but so I'm going to just kind of put officially on paper what we've been working with. When you have the antiderivative of a function, okay, the official notation now, okay, when you start with the regular letter f and not an f prime, so when you just start with the definition of f, okay, the rule, the way we communicate to each other that we're doing antiderivatives is to use the capital letter f. Okay, so the lowercase f indicates the original function, f prime indicates a derivative function, capital F indicates an antiderivative function. Right, when you write it like this, plus c, this is called an indefinite integral. Indefinite integral. It basically means it has no bounds. Okay, there's no lower number, there's no upper number, there are no bounds. Okay, so then the opposite of an indefinite integral is a definite integral. So I want you to go back to your fundamental theorem of calculus title, and I want you to add, definite integrals. So you've actually been working with the first part of the fundamental theorem without really even knowing it, because you were working with indefinite integrals with a plus c on the end. Okay, what we are doing now has an a and a b on it. So when you add the a and the b, the way we write that, okay, so that's a and b. Okay, our notation is capital F of x plus c. Okay, so you do the step of the antiderivative, and then you write it like this with a bracket on the end with a and b translated that way. Some books just use a straight line. Some professors, if you have like an old school professor, when you get to college, you might see him or her writing it just with a straight line instead of the little brackets. But the more customary modern notation is to write it with the brackets. So that's the step of calculus. The step of calculus takes one line, and that's usually it. After that, it's arithmetic. And what you do is you take the number b, which is your upper bound, and you plug it in to f of x plus c. F of b plus c. So you plug in the upper bound. Okay, minus, and then you'll do f of a plus c. So you plug in the upper bound first, and then you subtract when you plug in the lower bound. So the step of calculus is one step, and the step of arithmetic then is the rest of the problem.
So are we finding the range?
So what does this find? Not the range, but what this finds is the exact area bounded from the lower number to the higher number along the x-axis. So we've done this before. The Greeks, remember, would do it with rectangles. The Greeks would do it with trapezoids. Then we had Simpson who did parabolas. And then finally, Leibniz was the guy who figured out that the antiderivative area actually computed, the antiderivative actually computed the actual area, the exact value underneath. So when your calculator, when you type that into FNInt in your calculator and you're putting in the a and the b, this is what the calculator is doing. The calculator will determine the antiderivative, it will plug in the values, and then that's where it gets its actual number from. Yeah, Daniel?
Is it also solving for c then?
Okay, so that's a good question. Is it solving for c? No, it will not solve for c. C ends up to be irrelevant. What happens is, what do you do with that negative? What does it affect? Okay, it affects both of these. So, right, and so ultimately, the value of c for a definite integral, you have f of b plus c minus f of a minus c. So you just end up with f of b minus f of a, and the c's cancel each other out, and they end up being irrelevant to a definite integral. So c is part of an indefinite integral, but it's irrelevant for a definite integral. So let's just practice this. Okay, you've practiced antiderivatives now for 2 days in a row. So now let's put some numbers in, and this will actually compute area for us at the same time. So let's look at this question. Okay, the integral from -1 to 1 of the function 2x to the 4th minus 4x squared plus 2 along the x-axis. So if you are asked to draw the meaning of that integral, you would draw that function and you would identify the area that's trapped between -1 and 1 and the x-axis. So this function is a quartic function, which means it looks like a W. So the meaning of this function, the geographical visual interpretation, it peaks at 2 right there on the y-axis, but it has x-intercepts of -1 and 1. So the meaning of this would be the area trapped between -1 and 1 and the x-axis. And so we're looking at this area in here. So the value of this area is computed by one step of calculus and then a couple steps of arithmetic. So our step of calculus is to determine what the antiderivative of this is. So we're going to have 2x to the what power? 5 divided by 5 minus 4x to the power of 3 divided by 3 plus 2x plus c. And that will be evaluated from -1 to 1. And then your job is to plug in the number 1 first and come up with a value, and then number -1 second and come up with a value. So we will have, when we plug in the number 1, 2/5 minus 4/3 plus 2 plus c minus, and then when we plug in that value, we'll have -2/5 plus 4/3 minus 2 plus c, and then we distribute our negative, and then we clean up the math. So the calculus is one line, and the rest is purely mathematics and arithmetic. I like to group my fractions together. So I'm going to have 2/5 plus 2/5. That's a 2/5 from the front set of parentheses, and then minus the -2/5 from the second one. So I like to clump those together. And then I'll have -4/3 minus another 4/3. Okay, that's the -4/3 from the first parenthesis minus the second one. And then I'll have 2 plus 2 plus 2. And then I'll have the plus c, and then I'll have the minus c. So I clump everything together and then simplify. So I'll end up with 4/5 minus 8/3 plus 4. And for me, it's easier to do my math that way if I've combined like terms. And now I can get a common denominator. So my common denominator would be 15. So I'll end up with 12/15 minus 40/15 plus 60/15. So 32/15. So let's say that you're asked to evaluate the following integral using the fundamental theorem. So let's go from 4 to 7 and 1 over x minus 2, and then relative to the x-axis. So 1 over x minus 2 is a hyperbola. It's a hyperbola that's shifted 2 to the right. And so if I've got a graph, I know that 2 to the right is an asymptote. And then my hyperbola looks like this. I am limited. Well, okay, let me ask this question. I have to be aware of where my asymptote is relative to my boundaries. In other words, my boundaries could not go from -4 to 7. Because if I went from -4 to 7, I would cross over the asymptote, and I can't compute area if I'm up against an asymptote like that. So watch out that the bounds don't put you in violation of the domain. This domain is assumed that x could never be 2, and so your bounds could never include the number 2. So thankfully, this one we were just given 4 to 7. So if we understand what that looks like, okay, the number 4 is here, the number 7 here, and it's trapped above the x-axis, so we're looking at that amount of area. So our step of calculus should be one line and one line only. This integral should equal, okay, what is the clean antiderivative of 1 over x minus 2? The natural log. And then I'm old school, so I always have trained myself to put the absolute values around my natural log, plus c evaluated from 4 to 7. A question usually inevitably comes up, if I know the plus c is going to cancel out, do I still have to write it? And the answer is yes, you have to write it at least once. So here's the one time you have to write it. You don't have to show that it cancels out later, but it is part of the AP rubric in terms of scoring. They want to know that you know that it's there. And so they will dock you if you don't show it at least once in your work. Okay, once is all it takes, but at least once. So from this point on, I would say the natural log of the absolute value of 7 minus 2 minus the natural log of the absolute value of 4 minus 2, which is the natural log of 5. And I don't need my absolute values now that I've come up with a positive number, minus the natural log of 2, which if you remember your arithmetic properties, natural log of 5 minus the natural log of 2 is the natural log of 5 over 2. Okay, the subtraction of two logs is the logarithm of the ratio of those two. So that is the exact representation of the area that was shaded underneath that curve. Okay, all right, any questions on that so far? Yeah.
You don't need us to put a numeric value for that? Like,
This is a numerical value.
okay, so we can leave it like that.
This is preferable to the decimal because any decimal you would have would be a rounded value. And this is more accurate than a decimal. So it's preferable because this is called an exact answer. Okay, how about this? All right, the integral from -1 to 3 of x plus 1 cubed dx. So now we're dealing with a cubic. This cubic, so if we take a visual, the cubic has been shifted 1 to the left. So it'll look like this coming through -1. So there's my cubic. And I'm going from 1 to the boundary of 3, or excuse me, from -1 to the boundary of 3. So I'm going to run out of space here, so you'll have to forgive me, but my area would be going farther than that, but I'm going to run into my integral. Okay, now I'm ready for the calculus. My one step of calculus that I'm going to do. Is x plus 1 cubed an antiderivative that you recognize?
Should the power rule?
It doesn't work on an x plus 1 like that. Well, it does, but you need to know some other stuff first.
Multiply whole thing.
Okay, is that what you're thinking? All right, Abby, what are you thinking? Okay, so you want to superfoil that out. So you need to do some algebra first before your calculus. And so yeah, you're going to want to expand that. Whoops. So you're going to have this expanded to the integral of x cubed plus 3x squared plus 3x plus 1. So So you want to do a little bit of your algebra first before your calculus. So in this case, it was helpful, it was beneficial for you to do some algebra first. Then you can use the power rule on each term individually. So then you're ready for your calculus. And so x to the fourth divided by 4 plus 3x to the third divided by 3 plus 3x to the second divided by 2 plus x plus c, all evaluated from -1 to 3. And again, I've written my plus c at least once, and it's like, phew, okay, I'm off the hook. I don't have to keep writing plus c again. Then I will substitute in my, my bounce. So I'll have 81/4 plus 81/3 plus 27/2 plus 3. That's the number 3 plugged in. And then minus 1/4 minus 3/3 plus 3/2 minus 1. Yeah, Abby? Okay, any other major questions about that? Okay, if you wanted to check your answers tonight, I'd like you to do these without your calculator, but if you do want to check your answer, you could use the FNIT feature of your calculator just to make sure that you haven't made a computational error by mistake, but please do the majority of the work without it, without the assistance of that. You do not need to graph every time. You don't need, the graph helps me to see how my answer relates to what it actually means, but you are not required to do that. That just is it's a visual assistance that helps me. Glenn, did you have a question?
No.
Okay. Okay, anybody else? Okay, the homework is a little bit on the longer side. It's not hard, but there is the arithmetic that comes with it. So, if you thought like last night and the night before, you got your homework done in 15, 20 minutes, whatever, however long, or less, whatever it took you, this might take you a little bit longer because there is the computation that comes with it. All right, so good job. We're on the fundamental theorem of calculus. What, Bella? It is. But you got 2 days to do it. Oh.
It's okay.
Okay. Let's see.